AC or DC refers to the way electric current flows. AC, alternating current, flows in one direction, then reverses and flows in the opposite direction. Voltage level also alternates between positive and negative values. Commonly used in households, businesses, and power grids. Easier to transform and transmit over long distances. Can be stepped up or down using transformers. DC, direct current, flows in one direction only, from positive to negative. Voltage level remains constant, commonly used in electronic devices, batteries, and automotive systems. More suitable for short-distance transmission and low-voltage applications. Typically converted from AC using rectifiers or converters. Key differences. Direction of current flow, voltage characteristics, application and usage, transmission and transformation capabilities. AC is typically used for power grids and household electricity, industrial power distribution, motors and generators. DC is typically used for electronic devices, automotive systems, cars, trucks, etc. Renewable energy systems, solar, wind, etc. Battery-powered devices. Let's break down single-phase and three-phase power. Single-phase power. Single-phase power is a type of electrical power distribution that uses two wires, one hot wire and one neutral wire, to transmit alternating current AC. The voltage in a single-phase system oscillates between positive and negative values, creating a sinusoidal waveform. Advantages. Simple and less expensive to install. Suitable for residential and small commercial applications. Disadvantages. Limited power capacity. Not suitable for heavy industrial loads. Three-phase power. Three-phase power is a type of electrical power distribution that uses three wires, three hot wires and one neutral wire, to transmit AC. The voltage in a three-phase system oscillates between positive and negative values, creating a sinusoidal waveform that is offset by 120 degrees between each phase. Advantages. Higher power capacity and efficiency. Suitable for heavy industrial loads and large commercial applications. Smoother power delivery. Disadvantages. More complex and expensive to install. Requires more wires and equipment. Key differences. Number of wires. Single phase 2 wires vs 3 phase 3 or 4 wires. Power capacity. Single phase limited vs 3 phase higher. Efficiency. Single phase less efficient vs 3 phase more efficient. Three-phase power is commonly used in industrial settings, factories, manufacturing, large commercial buildings, offices, shopping centers, data centers, power distribution systems. Single-phase power is commonly used in residential homes, small commercial buildings, stores, restaurants, lighting and heating systems. When electricity is transmitted over long distances, some of the energy is lost due to resistance in the transmission lines. Let's use the voltage formula to explain why high voltage transmission is more efficient. V equals I multiplied by R, where V equals voltage in volts, I equals current in amperes, R equals resistance in ohms. When transmitting electricity over long distances, the resistance R of the transmission lines is constant. To reduce energy loss I squared multiplied by R, we can either reduce the current I or increase the voltage V. Let's say we want to transmit 1000 MW of power over a transmission line with a resistance of 10 ohms. If we use a lower voltage, say 100 kV, the current would be I equals P V equals 1000 megawatt, 100 kilovolts equals 10,000 amperes. Using the formula V equals I multiplied by R, the voltage drop, energy loss, would be V equals 10,000 ampere multiplied by 10 ohms equals 100 kilovolts. This means that 100 kilovolts of energy is lost as heat in the transmission line. Now, Let's increase the voltage to 500 kV. A equals PV equals 1000 MW, 500 kV equals 2000 amperes. V equals 2000 amperes multiplied by 10 ohms equals 20 kV. By increasing the voltage, we've reduced the current and subsequently the energy loss 20 kV versus 100 kV. This is why high voltage transmission is more efficient for transmitting electricity over long distances. High voltage transmission reduces the current flowing through the lines, which in turn reduces the energy lost as heat. High voltage transmission allows for more efficient transmission of electricity over long distances. This is because the higher voltage enables the use of smaller conductors, which reduces the weight and cost of the transmission lines. High voltage transmission lines have lower line losses compared to lower voltage lines. This means that more of the generated electricity reaches the consumer. High voltage transmission is more economical for transmitting large amounts of electricity over long distances. It reduces the number of transmission lines required, which saves on materials and construction costs. High voltage transmission systems are more reliable and less prone to faults, as they operate at higher voltages and lower currents. The most common high voltage transmission voltages are 115 kV, 230 kV, 500 kV, and 765 kV. These high voltages are stepped down to lower voltages like 120–240ths of a volt at substations before reaching consumers, ensuring safe and efficient delivery of electricity. HVDC high voltage direct current stations are facilities that convert alternating current AC to direct current DC, or vice versa, for the transmission of electrical power over long distances. They play a crucial role in modern power systems, enabling the efficient and reliable transmission of electricity across vast distances with minimal losses. Here's how they work. 1. Rectifier station. The AC power from the transmission grid is converted to DC power using a rectifier. 2. DC transmission. The DC power is transmitted over long distances through a DC transmission line, often underwater or underground cables. 3. Inverter station. The DC power is converted back to AC power using an inverter, which is then fed into the receiving grid. HVDC stations are used for 1. Long-distance transmission, reducing power losses during transmission over long distances. 2. Interconnecting grids, connecting asynchronous grids or grids with different frequencies. 3. Renewable energy integration, enabling the transmission of power from remote renewable energy sources, like offshore wind farms. The mechanical plant design team is responsible for designing the mechanical aspects of HVDC stations, including 1. Station layout design. 2. Building requirements inputs to civil designers. 3. Installation drawings and detail design of steel supports, connectors, insulators, etc. These designs ensure the safe, efficient, and reliable operation of the HVDC station. HVAC high voltage alternating current and HVDC high voltage direct current power stations are both used for transmitting large amounts of electricity, but they differ in the type of current used and the technology employed. HVAC power station. 1. Alternating current. Transmits power using alternating current AC. 2. Transformers. Uses transformers to step up or step down voltage levels. 3. Shorter distances. Suitable for shorter transmission distances up to 500 miles 800 kilometers. 4. Less expensive. Generally less expensive to build and maintain. 5. Wide industry adoption. Widely used in power grids worldwide. HVDC power station. 1. Direct current. Transmits power using direct current DC. 2. Converters. Employs converter stations to convert AC to DC and vice versa. 3. Longer distances. Suitable for longer transmission distances over 500 miles 800 kilometers. 4. Higher capacity. Can transmit higher amounts of power with less energy loss. 5. Specialized applications. used for specific applications like underwater cables, interconnecting asynchronous grids, or long-distance transmission. Key differences. Type of current AC versus DC. Transmission distance and capacity. Technology used transformers versus converters. Cost and industry adoption. HVAC is commonly used for local and regional power distribution, industrial power supply, residential and commercial electricity. HVDC is typically used for long-distance transmission over 500 miles, 800 kilometers. Interconnecting asynchronous grids. Underwater power transmission, example, submarine cables. High power transmission with minimal energy loss. The main differences between a high-voltage direct current (HVDC) power station and a low-voltage direct current (LVDC) power station are: HVDC power station. 1. High voltage. Operates at extremely high voltages, typically 100 kV to 800 kV DC. 2. Long-distance transmission. Designed for transmitting large amounts of power over long distances, hundreds of miles, with minimal energy loss. 3. Converter stations. Use complex converter stations to convert AC power to DC and vice versa. 4. Overhead lines or cables. Transmits power through overhead lines or underground cables. 5. High power capacity. Can transmit thousands of megawatt of power. LVDC power station. 1. Low voltage. Operates at relatively low voltages, typically up to 1 kV DC. 2. Short distance distribution. Designed for distributing power over short distances, within a building, campus, or local area. 3. Simpler conversion. May use simpler conversion methods, like rectifiers or DC-DC converters. 4. Cables or bus bars. Transmits power through cables or bus bars. 5. Lower power capacity. Typically transmits smaller amounts of power, up to tens of megawatt. HVDC is used for bulk power transmission over long distances. Connecting asynchronous grids, different frequencies or phases. Underground or underwater power transmission. LVDC is used for local power distribution, data centers, commercial buildings, etc. Renewable energy systems, solar, wind, etc. Electric vehicle charging infrastructure. Telecommunications power systems. In summary, HVDC is designed for high voltage, long-distance transmission, while LVDC is suited for low voltage, short-distance distribution. Here's an example of an HVDC, high voltage direct current, transmission system from a wind turbine to a home. Step 1. Wind turbine. A wind turbine generates electricity at a voltage of 33 kV AC. The electricity is sent to a nearby substation. Step 2. Substation. The substation converts the 33 kV AC to 150 kV AC using a transformer. The 150 kV AC is then sent to an HVDC converter station. Step 3. HVDC converter station. The HVDC converter station converts the 150 kV AC to plus or minus 300 kV DC using a thyristor-based converter. The DC power is transmitted over a long distance, example, 500 kilometers, with minimal losses. Step 4. Receiving station. The plus or minus 300 kV DC is received at another HVDC converter station. The station converts the DC power back to AC, example, 150 kV, using another thyristor-based converter. Step 5. Substation. The 150 kV AC is stepped down to 33 kV using a transformer. The 33 kV AC is sent to a local distribution grid. Step 6. Distribution grid. The 33 kV AC is further stepped down to 230 volts AC using transformers. The electricity is distributed to homes and businesses. Step 7. Home. The 230 volts AC is received at a home, powering appliances and devices. In this example, the HVDC transmission system enables the efficient transmission of electricity from a remote wind turbine to a home, over a long distance, with minimal losses. The HVDC system converts the AC power to DC, transmits it, and then converts it back to AC for distribution and consumption. A classic HVDC high voltage direct current converter station consists of several key components, which are typically arranged in a specific layout. Here's an elaboration of the components and their arrangement. AC yard, located on one side of the valve halls, includes switching equipment, example, circuit breakers, disconnectors, transformers, example, step-up or step-down transformers, extensive filtering equipment, example, harmonic filters, capacitor banks, capacitor towers for reactive power compensation. Purpose: connects the HVDC station to the AC grid. Provides voltage transformation and switching capabilities. Filters out harmonics and other disturbances to prevent interference with the AC grid. Valve halls. House the power electronic devices, example, thyristors, IGBTs, that convert AC to DC or vice versa. Typically arranged in a modular fashion, with each module containing a set of valves and associated cooling systems. DC yard, located on the other side of the valve halls, includes DC switching equipment, example, circuit breakers, disconnectors. Filtering equipment, example, DC filters, smoothing reactors. Purpose: connects the HVDC station to the DC transmission line. Provides switching and filtering capabilities for the DC output. DC hall buildings. House the DC switching and filtering equipment. Typically located indoors, adjacent to the valve halls. Purpose: provides a controlled environment for the DC switching and filtering equipment. Protects the equipment from harsh weather conditions and other external factors. Spare parts area. Typically located adjacent to the valve halls or DC hall buildings. Purpose: stores spare parts and equipment for maintenance and repair purposes. In summary, the classic HVDC converter station design features a larger AC yard with extensive filtering and switching equipment, a central valve hall area with power electronic devices, and a smaller DC yard with switching and filtering equipment. The DC hall buildings provide a controlled environment for the DC equipment, while the spare parts area supports maintenance and repair activities.